Our final speaker for the day is Dr. Andy Connolly from the University of Washington, where he directs the eScience Institute. Andy has been a major force in data science for a long time as an astronomer. He has been a significant part of the Sloan Digital Sky Survey over the many years that it has been a central resource for a whole field. And in that sense, he's a great resource to talk about the impact of data science on science and the history of data science and where it's going. So I'm looking forward to your talk. Thank you.
Thanks, Jack. Thank you. It's very kind. I have recorded how long you clap for at the beginning, and I will record how long you clap for at the end. Hopefully it'll be longer. So what I wanted to do is, it's been a total fire hose of information over the last couple of days. It's been really wonderful to see and hear about all of the research that's ongoing. I wanted to do a couple of things. I wanted to talk a little bit about how we as researchers and data scientists connect with different communities. So how do you build research across different groups? What are the mechanisms that we use? So how do we develop research communities? And how do you and I, as data scientists, engage in projects? What sort of projects can you work on? What impact can you have? And then I wanted to transition a little bit to talk about the application of data science and machine learning and AI, in particular in the field that's close to my heart, which is astrophysics. And the kind of key messages I want you to take away from this are that you don't always have to have a data-driven AI perspective to make progress in machine learning associated with different science cases. And in particular, that we can actually utilize, I think as we've heard over the last couple of days from some of the talks, we can utilize the symmetries within data. We can utilize the knowledge that we have about physical systems that we've built up over the last 100+ years to reduce the dimensionality of the problems that we're trying to solve. And this enables us to do much better in terms of the performance of the AI and the machine learning systems that we're working on. So I promise I will go fairly quickly because I know it is late. I just want to talk a little bit about some of the science that has come out of the eScience Institute, and in particular to highlight some of the research that we've done over the last 10 years that has been multidisciplinary, cross-disciplinary work. So this includes projects like deer fear. Deer fear was where we put accelerometers on deer, and we tried to understand whether they were foraging or whether they were resting or bedded or whether they were being vigilant because they had fear of wolves. And this was a project that was actually led by an oceanographer in terms of the data scientists working with the eScience Institute. We've worked on projects such as detecting wildflowers. And here we flew drones over the wildflowers around Mount Rainier. And the goal was to use machine learning and AI and image processing techniques to identify coverage and wildflower populations, and then use that information to calibrate satellite imagery, so spectral temporal satellite imagery to look at how the populations of wildflowers were actually impacted by climate change. We've worked on, and that one was a statistics and an applied math PhD who was working in that area, who was a data scientist at eScience. We've worked on NLP problems. We've worked on justifications for internment by analyzing the text from the British government for internments during the 1970s when they had the Northern Ireland during the Troubles. And how do governments actually justify the to themselves, how do they justify the abuse of their own populations? And that was done by a sociologist and an ethnographer. So the research that we do, the technical applications that we can apply, cover a broad range of science, of research, both in the perspective of kind of classical research, going all the way through to data science for good. Okay. And it's worth looking at how rapidly this has changed over the last 8 to 10 years. If you came in as a student today at the University of Washington, these would be the options that would be available to you if you were interested in working in data science. Whether it was applied in physics or biology, or whether it was one of the methodological fields in computer science or statistics. And you can see there are programs in graduate programs, undergraduate programs, professional development and masters. We have formal and informal education. We have a data science minor that was started about 3 years with a goal of pushing data science into the arts and the humanities. And that is now the third most popular minor on campus. And so there's an enormous amount of development of data science education. This is what it looked like in 2014. Okay, if you came on board, we were just starting up an NSF-sponsored graduate program for advanced data science. We were just spinning out professional certificates to teach master's programs in data science. When we think about universities, often universities are classed along the same lines as libraries and religions, in the sense that they never change. They last for hundreds, potentially thousands of years, and they just stay relatively the same. And so this sort of change in terms of the evolution of the education and how that education is spread across campus and not just focused in one or two individual departments is remarkable. And we're seeing that transition happening again as we move into developing educational programs centered around AI and machine learning. And so what I wanted to do is to look a little bit at how this changed, how this came about, and how this allows us to actually begin to engage with different research communities. And one of the ways that we've been doing this in particular at the eScience Institute is to try and find informal ways and look at gaps between both the education of different communities and also how we bring those communities together. And we run these programs such as office hour consultations. So the goal is to actually meet the research community, meet the biologists or the physicists or the oceanographers where they actually are, where they are at that time, and then to move them in the direction that they want to take their research. And so these office hours can be short-term engagements with people like Brynna Hazelton, whose background is in radio astronomy, but has a lot of expertise in machine learning and multicolor processes. And then you can engage with her for a couple of hours in terms of trying to move your project forward. If that is successful, or you need to have a deeper engagement, we run things like incubators. And these are 3-month-long engagements where you commit to work with a data scientist 2 to 3 days a week, and you work with them side by side. And the goal isn't that the data scientist will take your data set and maybe put it into the cloud or speed up your algorithm by factors of 10 or more. That is the result that we'd like to see, but the goal is that we educate the physicists, the biologists, or any of the researchers so that they take those skills back to their own individual institutions. And this is a wonderful way of engaging with a community. And the reason for that is because there are exit points, right? There are places where you, as a researcher, as a data scientist, can work with someone for a few hours, and you can see whether that project has potential to go further. You can work with a researcher for a few months, see whether that turns into an NSF, an NIH proposal. But it also allows you to have an exit point. And I think this is one of the things as a new faculty member that you really want to be thinking about is it's very easy, particularly when you come in with large numbers of, or large amounts of kind of technical skills, it's very easy to become overloaded in the work that you have. And so having the ability to both decide whether you're pushing a project forward on the long term or whether you can exit it is something that is a wonderful skill to have. And this provides you with the scaffolding. And some of these projects ended up going on to result in multiple papers. Ariel Rokem, who is a neuroscientist in the eScience Institute, he worked with Elizabeth Nance, who was a material scientist. And they worked on drug delivery into the brain. And they developed algorithms for particle tracking. And these particle tracking algorithms have led to new software that is widely used. They've led to grants. They've led to papers. And so you want to have the ability to have a progression of different outcomes. So short-term engagement, medium-term engagement, long-term engagement, where the length of the engagement is driven by both sides. Okay. The other thing that we found that's been really necessary and important for us is that when we have an engagement with a research group, we want that to be both open, we want it to be inclusive, and we want to be immersive in the sense that the engagement has to be authentic, right? And the reason for that is we heard today or yesterday about different kind of styles of researchers, whether you're a T-shaped researcher or a pie-shaped researcher or an octopus-type researcher, all different sorts of models. For me, I think it's more about linguistics. It's about learning the language. And I say that as a person who grew up with English, and my only claim to some form of multilingual ability is saying Z when I'm talking in the US. But we have to, it takes time to learn the languages. And I think, again, with the same model of a multilingual approach, once you've done it once, learning the next language and the next language becomes much easier. And so you have to allow it to be immersive, and you have to allow it to be open because you want what you develop to be visible to the community. But you also want it to be extremely inclusive because you want you want it so that any group can actually engage. And so we've been developing a number of programs associated with this. One of these is the idea around hack weeks. So typically, if you look in industry, a hack week is it's centered around some sort of prize-like structure, right? So you all work on a project. Whoever does best gets some prize at the end. And this isn't the model that we want to engage with. What we want is a collaborative effort where you come together as a group and you define what the projects are that you want to work on. And then over the next week, you have mixtures of lectures where you learn about the subject and projects where you work on in teams jointly to work and deliver solutions to the problems that you set. And so we've been building out these hack weeks and hack weeks as a service. And this happens in astronomy, it happens in ice sciences or water sciences. And there's a range of these different hack weeks that now become available across the US. We're now building that out as a service within the eScience Institute. So if you have a community that you want to create some sort of engagement or build some sort of interactive a program where you can all work jointly on a particular research project. We've been trying to spin that out in terms of providing people with the tools to be able to do that. And the important aspect that we found with this has been that you have to be deliberative in terms of how you select the people who come into the hack weeks. And we've developed tools that allow you to have a more equitable approach to ensuring that you have a diverse community who work within these hack weeks. We've also been working very actively on the impact of social good. So you, as I said at the beginning, many of the science cases or the research cases that I've talked about have focused around the societal impact of the data science research that we're doing. The program that kind of underpins all of this is a summer program that we run, which is the Data Science for Social Good program. It originated at the University of Chicago. We have taken this and turned it into a roadmap that allows others to build out these programs. And you're bringing together undergraduates and graduates and data scientists. And part of this is it provides an ability to bring people who maybe they come from the policy side and they're interested in understanding how you apply your data science skills to a particular project. And the projects are actually drawn from local government, from nonprofits. And in fact, one of the biggest challenges that we face today is to enable those nonprofits and those government organizations to think through what is the question that they want to ask, right? And how can you go about answering that? And to ensure they may have the data, but that data may not be in a form that it's accessible or it's easy to actually address the question that they want to ask of the data. And this is a significant amount of work, as we all know, as we go through the data munging and the data cleaning that we do in order to work on large data sets. And doing that for these organizations before you get into this program has been a challenge. And this is really what we're finding. This is limiting a lot of the nonprofits of being able to engage in data science questions and to be able to use data-driven techniques to answer some of their questions. But it's also been successful in different areas. I think my personal favorite one was one that started out from the Tasker Center for Accessible Technology. And this was an open sidewalks project. So the idea was Google Maps, but let's do Google Maps for people who have accessibility challenges. And so if you're in a wheelchair and you're going down a sidewalk, you need to make sure that the sidewalks and the path that you're taking have the appropriate ramps so that you can actually cross the street if you need to. It may be that you have to go into a building, go up a couple of floors, go across to the next building on some sort of skyway, and then back down. And this is the project that started out about 10 years ago. It's one of the first projects we did as Data Science for Social Good. And it then led, I think about a year ago, it led to about a $12 million grant from the Department of Transportation to trying to build out both a crowdsourced way to understand how do you get the data to be able to navigate if you're working with accessibility challenges, and also to build out the algorithms and the tooling to allow people to make use of this Google Maps-like infrastructure. Oops. The key aspect to all of this is when we talk about data science and big data, we often talk about it in terms of compute infrastructure. So are you running it on the cloud? Are you using GPUs? Are you training these large models? But the real infrastructure or the real power behind this has been the people. And the success of the investments in eScience has been the success of the people who underpin it. And so this is the group of data scientists that we currently have. You can see they come from a very diverse range of communities, whether it's from oceanography, whether it's from applied math and statistics, whether it's people who have spent 30-plus years working in Microsoft and different tech companies, whether it's people who have spent a few years at Amazon, or whether they've been working for their whole time in academia. It's this range of abilities and skill sets and interests, because these are not just people who have the data science capabilities. It's also that they have the ability to translate between different fields. And together, they can translate between different fields because they're in a common space where they can actually share and discuss ideas and allow one another to understand what are the technical challenges and what is the actual research goal of the community that we're working with. The other key aspects for what we try to do is when we're establishing ourselves as a data science community, we want to be neutral, right? We don't want to focus on one particular research area. We don't want to say that we are computer scientists or we're statisticians and you're coming to us in terms of we are the oracle of all knowledge and then you're coming in to work with us. We want to be neutral in terms of we're a community because we learn as much from engaging with different researchers in terms of the techniques that they're using and their applicability to other research fields as they learn from us. And the other thing that even in the era of COVID, it's still physical space, being able to come together, being able to communicate, and to do that as a community and not always through Zoom, even though Zoom is important, has been critical for the success of this. So I wanted to really pivot a little bit about where are we headed and where do I see data science heading and AI and machine learning. And there's two big areas that are very obvious at the University of Washington. The first one is common across, I think, all universities at the moment, the emergence and the desire to work at the interface of AI and machine learning. And that's what I'm going to talk about in the context of astronomy over the next few slides. But one of the things that we notice, and you can see this with this meeting that we set up in 2002, we set up a meeting, we brought together researchers from around the campus. Over 300 researchers came together who were working on AI and machine learning. They worked from weather forecasting through to the biophysics of different molecules and organisms. And what we've realized then was there were already 10 AI and machine learning institutes on campus, none of who apparently knew of each other. But bringing them together allowed them to start communicating and collaborating with one another. And so this is clearly a direction that we're driving in. The second one, which I won't have time to talk about here, is we've noticed that the growing reliance on data science is creating a similar reliance on software and software engineering processes. And in general, as an undergraduate or a graduate student, it is hard, even within an academic environment, to get access to learning the skills associated with developing software if you're anything other than a computer science student. And the reason for that is to be able to get to a point where you're taking courses on software engineering and software design, the prerequisites prior to that are so long that you just can't fit them in if you're also doing biology or you're also doing oceanography or physics. And this is a real challenge for us in terms of reproducible science, in terms of robust science, and in terms of us just being able to for the projects that we work on to last longer than the typical lifespan of a PhD project. And that is a huge waste of resources in terms of the development of data science and research. Okay. So now I just wanted to pivot a little bit to some of the things that we've been finding about in terms of the application of machine learning and AI. And I'm going to use astronomy as my example. Why am I using astronomy? Well, because I've worked on it for the last 20 years. But I'm also because if you look at where astronomy is going over the next decade, there are platforms or telescopes, both ground-based, such as the Rubin Observatory, which I'll talk about more in detail, which are going to be generating tens of petabytes of images per year. They're going to be imaging the sky, half the sky, every 3 nights, which means each night they're going to be detecting about 10 million moving, varying, changing in brightness, appearing objects on the sky, and releasing that out to the astronomy community for you or any other astronomer to decide whether you want to follow that up, whether it's an interesting project or an interesting object or not. It's very much like the Netflix problem. Not the Netflix problem that we heard about earlier today, but the Netflix problem that you have every evening where you go to your TV and you see that there are 1,000 possible channels that you might want to look at. And you have to, or programs you might want to watch. And you have to go through the exercise of, do I look at the same thing that I looked at last time? Do I look at the same category? Well, that's an interesting thing. There's a fair chance that I'll enjoy it, but the likelihood is I'm not going to learn anything new. Do I look at something random on the just pick one of the random programs? Well, I'll find something new, but the likelihood it wouldn't be that particularly interesting. So in astronomy, we have exactly the same problem, but we have 1,000 possible objects that we could look at, and we have to make a choice about which ones of those objects to choose. And to follow up a faint object requires a large telescope, and large telescopes cost anything from $50,000 to $100,000 per night to run. So there's a limited amount of resources. And then the other problem is that 30 seconds later, you're going to get another 1,000 objects. And then 30 seconds later, you're going to get another 1,000 objects. Every 30 seconds, you have to say, do I really want to look at this object? Do I still want to keep watching this Netflix show, or should I switch to another one? And these are the sorts of challenges that we face in terms of machine learning and classification. It's not just from the ground with Rubin telescope. There will be a Roman space telescope named after Nancy Roman, which will provide data sets which are smaller but much higher resolution from the ground. And the biggest kind of just to play on the last show, on the last talk from Tanya, the elephant in the room is the square kilometer array, which is a square kilometer of radio telescopes, which will generate about 5 terabits of data per second, which will be then converted into images, radio images of the sky, and generating a few 600 petabytes of data. So machine learning and AI has been integral in astronomy for many years, but mainly in the form of classification. Right? So here this shows you an example of a project that came from a citizen science project where individuals, hundreds of thousands of people, came and classified tens of millions of images from the Sloan Digital Sky Survey that Jack mentioned. And then we developed various neural network methodologies to do the classification. And they were extremely successful in terms of reproducing the visual classification with recalls of 85 to 95%, depending on the actual network that you're using. But that's only one aspect of what you really want to do if you want to advance research in terms of astrophysics and machine learning. So let me just see if I can get this to work. This shows you a video of the Rubin telescope that's going to start operating in about a year and a half. It's about 56,000 kilograms in weight. The mirror at the bottom is about 8.4 meters across. The mirror itself weighs about 15,000 kilograms. And yet this, as you can see, can move rapidly across the sky. It can be moved by 3 people. It sits on an oil bed, and it can be moved by 3 people. To drive it and stop it, it requires a significant amount of energy. It's equivalent to a small town. And so we have large banks of capacitors that as you slow and stop this telescope, that you regeneratively store the energy and then reuse it when you want to accelerate the telescope itself. One of the interesting challenges about this telescope is the 15,000 kilogram, 8.4 meter mirror. As you point to different parts on the sky, as you look at different elevations, gravity causes that mirror to sag. If the shape of the mirror sags and changes, then the image quality from this telescope degrades. And so at the back of this telescope, we have 156 actuators, force actuators, each one that applies between 1,000 and 2,000 newtons of force, which can bend the mirror, only bend it to about 100 nanometers in size, in deflection. But that is sufficient to change the quality of the images that you're actually deriving or getting from this telescope. Let me see if I can get it to move. The way you actually work out how out of focus this image is by taking the camera on the back of the telescope, which is 3.2 gigapixels in size. Looking at the edge of this camera, we have one sensor here. So each one of these sensors is just like the sensor you get in a digital SLR. So this camera cost about $187 million to build because it's extremely sensitive. And the quality of these sensors, which are about 4K by 4K in size, they're very sensitive from the ultraviolet through to the near infrared. And in these sensors, what we have is edge sensors where we shift the sensor a little bit, like 1.5 millimeters out of focus in one direction, and then 1.5 millimeters out of focus in the other direction. And this gives us a set of out-of-focus images. And these donuts are what we can analyze to measure the shape of the telescope and the mirror, and then apply corrections or different forces to get the image quality as accurately as you can. And this is the traditional approach that you would use. This is the difference or the change in the image as a function of how out of focus that image is. And what we do is we solve for this wavefront, and once you have this wavefront, you can correct the shape of the mirror. And it's a classic inverse problem. And there are standard algorithms that work beautifully and are used in the adaptive optics community, who correct not just for the shape of the mirror, they correct for the distortion of the stars due to the atmosphere. So the Nobel Prize a couple of years ago that was measuring the orbits of stars around the black hole at the center of the Milky Way, that utilized adaptive optics that could which could correct the sharpness of the images, so you can find the positions of the stars to an extreme degree of accuracy, so you can begin to measure how they move as a function of time. But the challenge with telescopes like this is, if you have an image, so this just shows you what an out-of-focus donut looks like, that's easy to analyze. But when you have them all overlapping one another, these traditional techniques, which take about 20 seconds to analyze a single image, they degrade rapidly, because you're trying to separate out an image that looks like this from something that has many overlapping images. Okay? And so this is where we begin to use the AI and the deep learning and the neural networks to classify these images to understand what is the underlying wavefront. And the power of these sorts of approaches is they are proving with training to be extremely robust to overlapping images. So the black here is the truth. These are amplitudes of angular Zernicke's. It doesn't matter what the signal is. The blue is what you would get from the traditional algorithm for this overlapping image. And the orange is what the machine learning approach achieves. What's particularly interesting is we started out by training these on a large number of simulations of the optics of telescopes, and then we moved over to these large image trained models, and we found that the large trained models with a small amount of transfer learning outperformed our own simulation-based networks, which for me was a little surprising, because this is different. When you have two stars overlapping, it's not like two chairs where one chair blocks out the other chair. So it's a different kind of physical model, and yet these large trained models actually were outperforming our large-scale astronomical simulations. And this work was done by John Franklin Crenshaw at UW. And the power of this was the improvement in image quality was about almost a factor of 2, as measured in terms of the residuals from these wavefronts. The execution time was a fraction of a second. It was relative to 20 seconds, and it performed much better in kind of these poorer observing conditions. And you can put a number on this, right? So it will cost this telescope about $57 million a year to run the observatory. And this approach will allow you to improve the number of fields where you can get good image quality will improve by about 6%. Okay, so you're seeing a $3 million return on the implementation of using these AI techniques in terms of the science that we're likely to get out. Okay. But more interesting is we're beginning to find that if we want to start understanding the science and the physics and the astrophysics, we have to start trying to understand the symmetries within the data. Okay? And so this is work that was done that started from an AI institute, the Dynamics Institute, that's led by Nathan Kutz and Steve Brunton at the University of Washington. What they were doing is they were measuring, they were trying to build a model that could predict the underlying dynamical equation for a nonlinear pendulum by taking sets of observations of a pendulum as a function of time. Okay? And they found three things. The first thing that they found was if you just worked in the normal space that you would think about, XY space, then you couldn't derive these dynamical equations. You had to change the coordinate system that you were working in into the angle of the pendulum and the length of the pendulum. So you had to find the right coordinate system that was appropriate for the physics of the problem that you were working on. If you did that, they found that you could use an autoencoder to reduce the dimensionality of the problem. They also found that you have to include in your loss function the actual dynamics of the system. But if you do that, if you include the dynamics and you include the appropriate coordinate system, then they found that by using a statistical technique that required or that imposes sparsity, they could, from a dictionary of possible dynamical models, they could actually select the appropriate model. And so this is telling us that we need to think about the geometries of the data and the natural coordinate systems, and maybe we don't need to just assume that the data will naturally discover that if we have a limited amount of data. And now I'm going to show you an example of how we think about this in terms of astronomy. So this shows you the trajectory of an asteroid as it moves across the sky. This asteroid is at a distance that is further away than the distance of Neptune. So these are a sequence of images, and you can see this asteroid slowly moving across the sky. And the traditional technique is you measure 2 points, you project it forward, you find the next set of points, you project it forward, and you build up an orbit. If you're looking for objects where you want to measure their motion over multiple weeks and potentially years, the interesting aspect is that and this really is kind of relearning 1,500-year-old physics. The majority of the motion that you're seeing is due to the motion of the Earth. So we see this retrograde motion due to the Mars, which comes about because Earth catches up with Mars. And so where you see Mars on the sky, Mars appears to go backwards. The Greeks interpreted this as if you required the Earth to be at the center of the system, the Greeks interpreted this as these epicycles, and that's what Ptolemy came up with. And then Copernicus and Kepler did more careful measurements and demonstrated that the appropriate system was a heliocentric system, and that enabled you to have a much simpler model. So you no longer needed a model that had prograde and retrograde motion with epicycles. Instead, you had this beautiful, simple, elegant elliptical orbit because you were working in the coordinate system that was appropriate for the data themselves. Perfect, thank you. And we've been doing this with astronomical techniques. So what this means is we project where the coordinate system, so in the same way I said that you move from the angle and the length of the pendulum, you now move to a place where you're observing as if you were at the surface of the sun. It's a lot warmer there, which if you come from Seattle is a good thing. But also it's a place where those orbits are now much simpler. And this is work by Joachim Moyens, who's taking a technique from this. And what he's demonstrating is that by changing by correcting for where the Earth is, taking out the motion of the Earth, these trajectories that you were looking for that were originally quite complicated now become very simple and linear, and you can use techniques like Hough transforms. So you can begin to use simple machine learning approaches because you've reduced the complexity of the problem. Why is it interesting? It's interesting because you get 20% more asteroids. Again, 20% on a $50 million project is quite a good return. The asteroids that Joachim is particularly looking for are the asteroids that may one day impact the Earth. So there are ancillary benefits if you can actually detect one of the 20% that may have impacted or may impact the Earth, as you saw with Don't Look Up. And also we use these techniques to track satellites. This is the impact of a train of Starlink satellites that have just been released a few days earlier. And this is an astronomical image And each one of these streaks is a Starlink satellite that is impacting your ability to see the night sky. Okay. We can take this a step further, and we can say, what happens if you can't even see an asteroid in an individual image? If you knew the trajectory of that asteroid, you could just take the images, align them, stack them, and allow you to detect a fainter asteroid. So you're essentially shifting and stacking the images, where you shift the images along the direction of the asteroid itself. The challenge here is it could be moving in any different direction, so you need billions of different computations of different trajectories, but you can use this with the GPUs that we all use for machine learning, and this allows you to search over very large distances or time baselines, and this is work done by Hayden Smotherman and Max West. Max West is a software engineer at the UW who sped up some of this algorithm by about a factor of 15 with a couple of weeks of work. And so the power of this is you can begin to look at, by transforming from a system where you would observe the asteroid, its motion as if you're on the Earth, to one where you're transforming to where you would observe it if you were sitting on the surface of the sun. You can see that all of these trajectories get linearized. It makes it much easier to find them. And this allows us to detect asteroids to much fainter than the detection limit of a single image, which is shown here. And this shows you the completeness of the numbers. So 80% of the asteroids have been detected, out significantly fainter than the detection limit of a single image. And this is work that's been done by David Gerdes and his group, including Kevin Napier, who is going to be one of the AI postdocs next year, and it's up in the audience if you want to know more about these data, these results. So the power of this is because it transforms the science that can come out of the Rubin Observatory. The Rubin Observatory expected to detect asteroids out to the distance of Neptune and discover about 20,000 of those asteroids. That compares to the 6,000 that we know today. So we're getting a factor of 5, potentially 10 improvement. If you can stack these images, you can then grow that out to another factor of 10 or more. Okay? So by using the data in an efficient way, using these machine learning techniques, we can actually begin to probe the outer parts of our solar system, potentially discovering planets like Planet 9 that a lot of people have been talking about over the last years. The cost in terms of the environment is significant, because it means that it would require about 10 million GPU hours in order for you to search the whole of the Rubin data set. But it would give you a census of the solar system that would allow us to understand how our solar system came into being. Did our solar system start from a double star? Did the large planets like Neptune and Jupiter, did they start much closer into the sun and then migrate out? How did our solar system evolve and form, which is something that we really should know when we're now talking about imaging in the next 10 years, imaging planets in external star systems. Okay. And so I just want to kind of bring it round to the question of how do we bring AI into this? And the key here is understanding what are the symmetries and what is the physics of the problem that you already understand. And this is work that was done by Kyle Boone. And this work centered on the idea of how do you measure the expansion of the universe? So how do you measure dark energy? The Nobel Prize for Dark Energy came about because people measured that the universe was expanding a little more quickly than they expected. And that was because the objects that they were observing were a little fainter than they expected. And these objects were supernovae, so the deaths of the final stages of white dwarfs, or the end stages of stellar history. The big challenge with that is some supernovae have the same brightness, they're standard candles. Most supernovae do not. And so what you want to be able to do is to separate out one from the other. The traditional way to do that is when you detect a supernova, you follow it up with a spectrum from a large telescope. As we said, those large telescopes cost you $50,000 to $100,000 a night. There's a handful of them in the world, limits the number of supernovae you can follow up. The second challenge is, if you want to classify this supernova, this is the light curves, how the brightness of a supernova changes as a function of time. It's a beautiful light curve, but most of these light curves, because we can only observe during the night, unlike radio astronomers, there is cloud, even in sites that are different from Seattle. The data that you get is very sparse. And so you have to be able to learn what type of supernova you're looking at. And what Kyle recognized was we know how to shift a spectrum given its distance. We know how to apply things like redshift. We know how a supernova or the brightness will dim with distance. We know how to convert a spectrum into the measurement of the brightness at a particular wavelength. But what we don't know is what are the intrinsic variability and the intrinsic properties of the supernova. So if you separated what we know, this physics layer, from what we don't know, you could reduce the dimensionality of the problem to a handful of dimensions. So the latent space here is 4 or 5. And the beauty of that is now you're learning a low-dimensional latent space, and that allows you to improve the classifications by almost a factor, when you're looking at great distances, almost a factor of 2 or 3. And so the purity of your sample is sufficient that purely from the observational data, without having to get and go and take a spectrum, you can get about only a less than a 5% contamination in terms of the supernovae that you're identifying as these supernovae with the same brightness. And that changes the science that you can do. Okay? So I just really wanted to kind of conclude with a couple of statements. One is that as data scientists and as part of the data science community, whether you come from the method side or whether you come from the applied side, the type of research that will be available to you over your kind of working lifespan, whether you're in academia or in your industry, is going to be incredibly broad. Whether this is applying machine learning or data science or AI. Understanding how you communicate with other research fields and understanding how you gain their language so that you can collaborate together is a comparable skill to learning the technical techniques that you have learned in abundance. There is a huge amount of places where you have the opportunity to engage with researchers and other researchers in other fields, whether it's from understanding natural language processing applied to understanding some of our societal issues, like we had with the analyzing the government records of people that they'd interned in Ireland, whether it's searching and developing algorithms and approaches for tracking wildlife, as Tanya was talking about, or whether it's applying it to specific astrophysical problems. And so the intersection of AI and data science remains a very open and interesting question. But the thing I would like to encourage you to think about is to use a lot of the techniques. I gave an example of physics, but the same in biology. Use the science that we've learned over the last 100+ years to guide some of the machine learning models that you might want to apply, because the benefits are that you can reduce the dimensionality of the problem that you're trying to solve, and that data-driven approaches have been transformative in research and science, but data-driven isn't the only way to go. And so I think there's a huge amount of interesting research and benefits from going to these physics-inspired or physics-informed models. And then I think it's, I just end, as I know I'm the last speaker here, to just say it is a really remarkable time to be a researcher. Whether you're in industry, whether you're in academia, there are huge challenges that we face about the societal impact of things like AI and machine learning. But it is rare that you get to live and work in a time when there is the potential for such transformative technologies. And I think that is something that we have a responsibility to drive it in a way that the science and the research and the impact on society is responsible. And it's you who drives that. I think we can't separate ourselves from the application of the techniques that we're using, but it still has the potential to have enormous impact on ecology, on astronomy, across many fields. And I will stop there. Thank you.
Questions? Oh.
This is like an incredible overview of the kind of work you're doing, so thank you so much for sharing this. One of the things I want to ask about is, how do you think about accountability mechanisms in the creation of these kinds of collaborations such that you can maximize the productivity, or at least to some extent ensure like they're a reasonable track of to success for such projects? Because what I've seen is a lot of times like collectives emerge and like people get together, but like it's hard to track progress or like ensure that there is some tangible outcome of these things. So thank you.
That is a really fascinating question. I think that is a question that goes beyond the data science. So there are many questions such as and this is something that you learn as you go through, admittedly not particularly successfully for myself, is when to allow a project to end, right? And so that is a challenge. And so I think things like these mechanisms where you can have a short engagement and then a long engagement, and there's a natural place where it ends, if you want it to, is good to have at the start. So if you say, I'm going to work with someone for a quarter or a semester on a project, and then I'm going to reevaluate, that's a nice way of having a place where you can both decide that it's not going in a particular direction. I think there's actually, with the software engineering teams that we've been building out, there's a lot that you can learn from the way that industry works, that some of that, not all of it, but some of it can be helpful in research. And one of them that we found particularly helpful has been to write down early on in the project, what are your user cases and user stories that you're trying to solve? And this is kind of coming from if you come from more of a software development background, then it's talking to the crowd. But from an astronomy and a physics background, writing that down rather than allowing the science to just meander, which is fine to do, right? But it provides a little bit more structure to it. And then I'd just say that we still face these problems. I mean, when we talked about hack weeks, we've been running those for about 5 years. We've run them in person. We transitioned to running them on Zoom, and that kind of dynamism kept it going. But now we're coming back in person. We're beginning to revisit what is actually engaging for a week as a community the right thing to do, or should you do that over multiple times over a year? And so you're continuously having to evaluate. But I think writing down what your goals are and having specific times when you're going to evaluate whether it's been successful and whether you want to continue is a good way of doing it. The other thing that's really important is to write down what your expectations are for credit associated with that work, so that everybody knows if you make a contribution and it turns into papers or publications, who gets credit in those publications, if it turns into patent applications, if it turns into a grant, how is that credit actually going to be defined? And that's one of the things we do in eScience when we run any of these engagements. We have a written description of what our expectations are, that we're not providing you just with, it's not like a service that you can go off and do, you get to, it's not like you're putting a quarter in and you're getting something out. It's actually a collaborative effort. That's what I'd say. Okay, sure.
All righty. So I think we are going to, I'm sorry. Was there someone else? Okay.
Yeah, quick question. You talked about learning the language of data science for like folks from physics or biology, and same is true for the other way around, people who are coming from data science and coming to physics or biology, healthcare. So how do you propose for these people, or for example me, how do we gain skills to learn the language of what a physicist speaks? So how is that collaboration done?
I think some of it is just time. I mean, we found that in our interactions, it would take 6 months of real engagement, unless there was some real low-hanging fruit. Then there was 6 months of engagement where you are talking and meeting weekly. And that's what worked for us. I think one of the nice things is that as the physics and biology and other communities become more versed with the data science languages, then they can actually meet you earlier and then help you with the work. It takes time, right? It takes time to learn biology. I don't know how long it took you before you felt like you were having an impact on the actual ecology side.
So for team scientists and interdisciplinary team scientists, team scientists and interdisciplinary team scientists who do these kinds of evaluations and specifically facilitate and have done this very early on, but starting with Centers for Clinical Translational Science, which are NIH-funded kind of interdisciplinary research centers, have shown that it takes about, you're spot on, 3 months to gain the language, 6 months, about half a year to gain language comprehension, to be able to talk to each other, and in about another 6 to 8 months to define a problem. So it takes about a year, if you're starting from zero both ways, where you are able to actually identify a question and start to working on a problem that both agree, yeah, that's the question we're asking and the problem we're solving. And then there are all kinds of estimates like this of like how long it takes to result. So interdisciplinary science takes longer.